My name is Abhishek Tiwari. I am affiliated with Indian Institute of Technology, Roorkee, India. In the present work, we are talking about a new approach for predicting low thermal conductivity transition metal oxides. We are interested in oxide thermoelectric materials for which we require low thermal conductivity oxides because the thermoelectric efficiency is inversely proportional to thermal conductivity. One of the major issues with oxide thermoelectrics is that they have usually very high thermal conductivity. So that's why we are interested in these compounds. And with that, actually, we are also trying to address one of the problems in materials informatics, which is of small data sets. Usually, the data sets which we have in material science are small. That is why which affects the accuracy of the machine learning algorithms. So in this work, we have proposed a two-step machine learning algorithm where we use selection and then regression steps to increase or basically to improve the accuracy of machine learning methods. In the next few minutes, my colleagues Siddharth and Nitish will be explaining the computational methodology which we have adopted in the present work, and then Nitish will be explaining the results which we have got. And in the end, I will again try to conclude and tell you what are the major findings from our current work.
As far as our methodology is concerned, we have proposed a two-step machine learning based process, which in the first step filters out unknown compounds having low thermal conductivity. This can be performed for any class, and in our case it was compounds having low thermal conductivity. So this classification is done only on the basis of fundamental material properties such as details about the interatomic bonding, the physical structure, and the compound chemistry. So this task is achieved through building a ternary classifier, and we were able to test out the performance of a large number of both machine learning as well as deep learning classifiers. Now in the second phase, we only consider compounds which have already been classified as having low thermal conductivity in the first step. So we built regression models on this data set, this filtered out data set would be better to say. And once again, we tried out a number of both machine learning as well as deep learning models to estimate the exact value or the numerical value of thermal conductivity of unknown compound. This process builds regression models which are multi-fidelity models because they are both accurate as well as computationally inexpensive to run, hence they are multi-fidelity models.
The data set used in our analysis had 314 observations and 9 variables. The classification phase involves categorizing the compounds into 3 classes of low, medium, and high thermal conductivity. We built about 30 machine learning models for the classification phase and found that XGBoost performed the best. Another startling discovery is that XGBoost gives an accuracy of 96% when trained on just 3 fundamental features. These fundamental features play a key role in material design. Now we come to the last phase of regression, where we build models to compute thermal conductivity. Here we found qubit regression to outperform a host of regression models. Also, when we introduce 2 new parameters, namely the Debian temperature and the Gruneisen parameter, the performance of qubit regression improves significantly.
In the previous discussion, we explained you the computational methodology, two-step process which we have developed, which we have proposed in this current work, as well as some validation results of that on oxide thermoelectric materials. What I can say is that because of classification step, we are able to reduce the variance in the data, and by reducing the variance, we are able to achieve higher accuracy in the predictive models. For example, in this case, we have predicted the thermal conductivity of oxide materials with a higher accuracy of high R square value of 0.9. Future outlook of the current work can be that it can be easily combined with high throughput computational material science and machine learning methods to predict the properties of interest, and we will be continuing our work in that direction. If you have any questions with regards to current work as well, or methodology or the results, you can always contact us through our email IDs which are given in the poster. Thank you very much.